Welcome to Lecture 9 of Modeling and Simulation of Physical Systems, in which I shall introduce you to the methods and techniques of modeling electrical systems. I will focus on the linear electrical circuits, which consist of passive linear circuit elements such as resistance, capacitance, and inductors. And they are connected in a circuit that is powered by some voltage or current source. In practice, however, we need to include some active elements to implement interesting real-life applications such as filters and controllers. An example of an active linear component is well-known operational amplifier when it is used as a linear device. Let's begin with an example of a circuit that we have already analyzed in our lecture 2. The problem asks us to relate the input voltage E with the output voltage E2 across the capacitor in a differential equation. The solution to this circuit becomes immensely simplified if we can convert the given circuit into an equivalent Laplace circuit. The Laplace circuit replaces each circuit component with its corresponding impedance. So remember, in the concept of impedance that was covered in the electric circuit course, we learned that impedance is essentially a frequency-dependent resistance. For instance, the impedance of the capacitor is when you take a Laplace transform for this component to calculate the impedance, that is actually 1 over S times C, where S is a Laplace variable that encapsulates the concept of frequency. The impedance of inductance is simply S times L, and the impedance of resistance is just that remains unchanged. This remains R. So when converted to the Laplace circuit, we notice that the resistances remain unchanged. The impedance of the resistance is the same as resistance itself. On the other hand, the impedances of the capacitors have been calculated as 1 over SC1 for capacitor C1 and 1 over SC2 for the capacitor C2. Furthermore, we should also convert all the time domain current and the voltage quantities into equivalent Laplace variables. So if ET represents the input voltage, that is the voltage used to power the circuit, then we should also convert this into Laplace variable. So now the voltage is a function of S, not T. And the same goes for E2 of T, that should also be converted into E2 of S. The most remarkable attribute of this approach is that once we have the Laplace version of the circuit, it becomes a lot easier to analyze the circuit, because that is when we can apply the basic circuit theory techniques such as Kirchhoff's current law and Kirchhoff's voltage law. Furthermore, we can also simplify the circuit by calculating the equivalent impedance, following the rules that we know for the calculation of the equivalent resistance when resistances are connected in, for instance, series and parallel. For example, here we can see that the two impedances R2 and 1 over SC2, they are in series, so we can just calculate equivalent impedance by summing the two. Likewise, the equivalent of these two impedances comes in parallel with the impedance 1 over SC1, so we can calculate the parallel of two impedances by using this formula for the parallel combination of the two resistances, as shown here. Therefore, by applying the techniques for the basic electric circuit theory for the case of impedances, we can say that if, for example, we wish to apply the KCL, and we take this as one of the nodes where the KCL needs to be applied, then we can just simply say that the current leaving this node, this current, and this current, the sum of these three currents should be equal to 0. So therefore, the first part of the current, let's say I call it I1, is this component, and I2, the current that is flowing through the impedance ZC1, that's the capacitor, so E1 over ZC1, and the third component I3 is this part, E1 over E1 divided by Z2 plus ZC2. Then because we want to relate the output voltage E2 across the capacitor with the input voltage, so we need to eliminate E1. This is our goal. We wish to eliminate E1 from the equation. For that, we realize that if E1 is the voltage of this point with respect to the ground, we can just say the common point over here is ground. So therefore, we can apply the voltage divider rule and say that the voltage across the capacitor by Kirchhoff's voltage law, so E2 of S, will be a fraction of voltage between these 2 points, and that comes from the voltage divider rule, or simply KVL, that is ZC2 divided by Z2 plus ZC2 times the total voltage between the terminal plus and minus as shown here. From this point and onward, we can just simply solve the two equations that we have developed, the first one from the KCL and the second one from the KVL. We can simply substitute the value of E1 in the Laplace domain, E1 of S equals to 1 plus S times R2C2 whole multiplied by E2 of S, and put that into 1. This will give us this new equation that only contains variable E2 and E. Simplifying this expression, we get R1, R2, C1, C2 multiplied by S squared plus R1, C1 plus R1, C2 plus R2, C2 multiplied by S plus 1 whole multiplied by E2 of S equals to E of S. So at this point, we have obtained a relationship between E2 of S and E of S in the Laplace domain. And now it is time to convert it back to the time domain representation. For that, we need to calculate the inverse Laplace. And for that, I would like you to recall the relationship between the differentiation in time domain and in the Laplace domain. So we say that S to the power n multiplied by some Laplace function. If you take an inverse Laplace, you are actually taking the nth time derivative of that function. Let's say x of s in Laplace, so that is going to become x of t. In our case, however, we have terms like s squared times e2 of s and s times e2 of s. So taking their inverse gives us the second time derivative of e2, and in the second case we get the first time derivative of e2. And the final term e2 of s has inverse Laplace, that is just e2 in time domain. So now we can obtain the differential equation as required in the question, and here's the differential equation, and we have arrived this differential equation rather indirectly. We have first developed the Laplace relationship between the quantities E and E2, and once we have that relationship, we applied inverse Laplace to arrive at the following differential equation. However, note that you could have obtained the same expression by directly solving the circuit in the time domain as given in the question. However, this provides an alternative solution and also an alternative approach which can be helpful in a lot of different complex scenarios. Situation in which this approach becomes particularly helpful is when we are interested in developing the state space representation of the electrical circuit. So for example, from the differential equation that we have developed in the previous slide, we can also derive the state space representation. For example, we can choose the state variable as E2 and its derivative E2 bar. Now in this case, I'm not going to assign new variables such as x1 and x2 as has been our convention in the previous lectures. We can still do that. But I think in this case, I would just like to work with E2 and E2 dot. These are going to be our state variables. And the state space representation can be easily derived from the differential equation that we have derived in the previous slide. So this is going to give you matrix A of the state space representation, and this is going to be matrix B. And likewise, the output was the voltage across the capacitor E2. That's the matrix C times. Therefore, this is going to be matrix C. And this is matrix D, essentially 0. So let us take some time to think about what does each state variable represents. E2 represents the voltage across the capacitor C2. That's this voltage. What about E2 dot? Well, E2 dot, suppose I could multiply the rate of change of the capacitor voltage, that is basically E2 dot. So if I multiply this E2 dot with C, that is essentially the current to the capacitor I2. So if I have to indicate what is the current to the capacitor I2, that is C times E2 dot. In other words, I can also say that this E2 dot is the current of capacitor C2 divided by the capacitance. However, what if I want a state space representation using different set of state variables? The migration from one state space representation to another is very helpful in the simulation of electrical circuits. That's because if the user is interested in the voltage across capacitor C2, but not its current, rather in the voltage of the other capacitor C1. Suppose now that we need a state space representation to solve this problem. For that, we need to define the state variable as the voltage across capacitor C1, that is E1, and the other state variables remain the same as E2. So how do we transform our old state space representation into a new state space representation in which the state variables are different, E2 and E1, the voltages across the capacitors? So the procedure will be follows. Let X, capital X, contains the old state space variables E2 and E2 dot, that was representing the voltage across capacitor C2 and the current to the capacitor C2 divided by its capacitance. And vector Y contains new state variables. We need to relate Y with X using some linear transformation. By that I mean the new state variables must be represented as linear sum of old state variables. So because it is easy to see that E2 has been preserved in this transformation, so E2 is just E2 as before. But what about E1? So for E1, we need to develop the linear relationship with the old state variables. So we know that E1, which is the voltage across capacitor C1, is a sum of the voltage across resistance R2 and the voltage across capacitor C2, that is E2. That can be easily derived with the help of Kirchhoff's voltage law as written here. So the voltage across resistance R2 is the current through the capacitor, which is the same as the current through the resistance. So the current in this branch is the same, IC2 multiplied by R2, and this voltage is added to the voltage of capacitor C2. So this is a linear relationship that can be used to relate the old state space variables with the new one, that is E1. We can also convert that transformation into a matrix representation. T relates new state variable vector with the old state variable vector x, and T in this case is 2 by 2, 1 0 1 R2C2. So once we know what is our transformation matrix T, once that is known, we can simply convert our old state space representation into the new state space representation, in which the state variables are contained in vector y. So we say that y dot equals to a prime times y plus b b prime times the input, that is e of t. The output e2 is c prime times y plus d prime times e2. Okay, what is a prime then? A prime is t times a times t inverse, where a is the state space matrix for the old state space representation, and b prime is the transformation matrix multiplied with the B matrix of the old state space representation. Likewise, C prime is C of the old state space representation multiplied by the inverse of transformation matrix, and D prime are essentially the same. As part of your homework exercise, you are required to show that the new state space representation is follows: the matrix A, which is A prime in this case, B prime, C prime, and D prime, and this whole state space representation is essentially the same as derived for the same circuit in the textbook. The state space equations are given in equation as 4.93 and 4.94 of the textbook. At this point, I should note that the state space representation given here can be derived directly from the time domain analysis of the circuit, the same circuit, but the method and the approach given here can be more intuitive and more general. The students can choose any method they feel they find easier to follow and they feel comfortable working with. Homework exercises. For the two circuits given here, you are going to develop, for the first one, circuit 1, develop the state space representation using capacitor voltage as one of the state variables and inductor current as the other. The other circuit is a bit tricky, in which the position of inductor has been slightly adjusted, and you should try to develop the differential equation representation of the circuit that relates the input voltage with the voltage of the capacitor, Vc of t, and then try to convert this differential equation into state space representation, and let me know what electrical quantities does each state variable represent. All right, moving on to the op-amp circuits. The op-amp is essentially a non-linear device. However, when used as a linear electrical circuit component, it is used as a negative feedback mechanism. So schematically, we have an op-amp which has a negative and a positive terminal. The voltage at the negative terminal is Vin minus, and that on the positive terminal is Vin plus. The output voltage is V naught. In its model, we say that the output voltage is G times the difference of voltage at the positive and the negative terminal, essentially Vin plus minus Vin minus. So this is how the difference goes. Important consideration: theoretically, the gain approaches infinity. The input impedance is infinity, and the output impedance is zero. What do we mean by that? Well, so the gain approaching infinity essentially means that the 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 op-amp must have some kind of a negative feedback in when used as a circuit element, such as shown here. So in this case, a negative feedback is provided by means of some impedance Z. What about the input impedance taken as infinity? Essentially, it means that there is no current that can flow inside the op-amp. So the current entering the op-amp is zero either through the negative terminal or the positive terminal. So the current is taken as zero. Unless the terminals are connected to some current source, which is a kind of a scenario that we shall not take into consideration or discuss in this lecture. A consequence of all three attributes of the op-amp model is that op-amp must be used as some negative feedback, as shown here, when used as an active linear circuit component. And the other attribute is that the voltage at the negative terminal will be the same as the voltage at the positive terminal. So therefore, the negative feedback is crucial for the linear operation of the op-amp circuit. And once we have a negative feedback, even if we provide some positive feedback, in this case, the positive feedback is provided by means of some other impedance such as Z2, we still have V in minus same as V in plus. Let's take a look at a quick example of a simple op-amp circuit in which the positive terminal has been grounded. So V in plus is zero. And then we have a negative feedback as expected. So that as a consequence, the V in negative, the voltage at the negative terminal is the same as voltage at the positive terminal. So V in negative is zero. That's because V in positive is grounded. And then there's some external voltage V1. That voltage V1 obviously with respect to the common ground. So we can say that V1 is a voltage of this point with respect to ground. And there's an impedance Z1 between the terminal at which the voltage V1 is applied and V in minus. And Z2 provides a negative feedback. It connects the output voltage with V in negative. The analysis of the op-amp circuit is particularly easy. In this case, we can see that we can apply the KCL. So the current entering the negative terminal is the current that has to leave from the negative terminal, essentially because there's no current that is allowed to enter the op-amp. So the current entering the op-amp is zero. So apply the Kirchhoff's current law. We get V0 minus V in minus divided by Z2. That this is the current passing through this branch. Call this I1. And we have the other component of the current, that is the current that is leaving. In fact, this current will be in the opposite direction. So I2 is this current. So this I2 is this part. So the sum of the current entering the node should be equal to zero, which essentially gives us this relationship V0 over V1 is equal to minus Z2 over Z1. This is a typical configuration of an inverted op-amp circuits. So for example, if for example Z2 is some resistance R2 and Z1 is also some resistance R1, then the ratio of the two resistances provides the amplified gain, and that's because V0 over V 1 is minus some resistance R2 over R1, assuming that R2 is some resistance, some impedance, Z1 is some impedance, and this negative sign can be eliminated by adding either another stage of an op-amp after this, or we can just, if we're smart enough, we can just use the non-inverting terminal. In that case, this whole thing is added to 1 without having another stage connected to this circuit. So anyway, so in this case, V naught can be made multiple times higher or lower than V1 simply by adjusting the values of resistance R1 and R2. Now let's consider an interesting circuit known as the Chebyshev second order low pass filter. So the low pass filter eliminates the high frequency signal components from the input signal. So that's where the filtration becomes very helpful, and is also used to eliminate high frequency noise from the signal. The circuit is shown here. So we have input voltage that needs to be related with the output voltage. That's how one type of problem can be posed. But in this case, the problem really asks us to develop the state space representation in terms of the voltages across the capacitor C1 and C2. So in order to solve this problem, we note that there is a negative feedback, and the negative feedback is connecting the output voltage to the negative terminal of the op-amp. So Vin minus equals to V0, that is very obvious. And because there is a negative feedback, therefore the Vin negative is also equal to Vin positive. So this is the most crucial observation in this whole problem. Define voltage V12, which is the voltage at this point with respect to ground, and apply the Kirchhoff's voltage law. We say that, so if we apply Kirchhoff's voltage law around this loop over here, and forget whatever that is inside. So starting from this end, this is minus V0 plus Vc1, that is this guy, plus V12 equals to 0. So this is the Kirchhoff's voltage law equation. And this gives you V12 equals to V0 minus Vc1. Then the other equation is the Kirchhoff's current law. So we say that C2 times Vc2 dot, that is the current through this branch, that is the current through capacitor C2. So IC2 is this quantity, C2 times Vc2 dot equals to the current that is passing through this resistance. So if we apply KCL over here, then the current entering this node is the same as the current leaving this node. So we know that the current leaving this node is C2 times Vc2 dot. But what about the current entering this node? Well, that is the voltage across this resistance R2, which is V12 minus Vc2. So V12 is V0 minus Vc1 minus, and then then we need to subtract Vc2 from that, so we get this expression. So now we have the two equations, this one and the other equation that we have used already, by the way. So that's V12 equals to V0 minus Vc1. But the important thing to note is that V0, as we saw, is same as Vin minus, is same as Vin positive. And Vin positive, what is the voltage over here? The voltage over here is same as Vin negative, which is same as V0 or Vc2. So the voltage at this point, let me do that again. So what is the voltage at this point? The voltage at this point can be either Vin, we say that Vin positive is same as Vin negative, that is V naught. But we have also said that this is the same voltage as the voltage across capacitor C2, so that is VC2. Therefore, if V naught is same as VC2, so these two terms will cancel out and we arrive at this expression. VC2 dot is minus VC1 over R2 C2. We have attained one state space equation in the form of the voltage, the derivative of the voltage across capacitors VC2. We next want to obtain the state space equation containing VC1 dot. So that is our other state variable. So VC1 dot multiplied by C1 gives us the current through this capacitor flowing in this direction. So this is the current shown here. That can be easily computed with the help of Kirchhoff's current law. So the current through this branch is the current over here and the current over here. So the current entering this node over here at this point is the current that goes through R2 in this direction and the current that goes through R1 in the opposite direction. Those currents can easily be written as follows. So V12 minus V in. So we're talking about current here, V12 minus V in over R1 plus the current through R2 in the opposite direction. So that's V12 minus VC2 over R2. And we know that V12 is nothing but V naught minus VC1 and V naught is just VC2 minus VC1. So we can substitute V12 as VC2 minus VC1 in this form over here and over here. And after some cancellation, we arrive at the second state space equation, that is VC1 dot, as shown here. So VC1 dot is minus sum of 1 over R1 C1 plus 1 over R2 C2 times VC1 plus 1 over R1 C1 times VC2 minus 1 over R1 C1 times V in. So what we have shown here is that the derivative of the state variable VC1 is a linear sum of the state variables and the input. So we can summarize the state space representation in the form of matrices A, B, C, and D. As a homework exercise, you are required to develop the differential equation as well as the transfer function representation of the same circuit implementing the Chebyshev filter. All right, our final example is the solenoid driver. And before I begin describing the circuit, my sincere apologies for such a poor handwriting. That's because it was the first time I was using digital pad to make my slides. All right, look at the circuit here. Again, op-amp used with the help of a negative feedback, and this time there are two components connected in parallel: the resistance C, the capacitance C, and the resistance RF. The voltage at the output of the op-amp is E naught, but the output is also connected to the load. So this RL series circuit is representing the solenoid. So RL series circuits are often used to model the solenoids, the toroids, or to model the electrical wiring or the electrical coils that we find in the actuators such as DC or AC motors. The input is fed to the negative terminal by means of resistance Ri, and we are required to develop the transfer function between the current IL, which is the current that is passing through the solenoid, and the input applied voltage EI. Solution. Again, V in negative is same as V in positive. That's 0. That's because V in positive is 0 over here. So we can apply the Kirchhoff's current law at V in negative. And for that, once again, I would like to take I would like to convert this circuit into an equivalent Laplace circuit. So I would like to calculate. I would first like to convert this into the impedances. This is 1 over SC and this is RF. So the parallel combination of RF and 1 over SC will be equal to RF divided by SC plus RF plus 1 over SC. So if you simplify this SC will cancel out and you get something like this. So this is the current. This whole expression represents the current which is flowing downward over here, and the current that is so this is the current which is entering this point, this node over here, and the current which is entering from the other end, that is EI minus 0 over RI, is this part. So this part represents the current which is entering this negative terminal. But remember, no current enters the op-amp, so the sum of these two current must be 0. So this represents our first equation. The second equation is very easy to develop. So this is just say that E naught, the output voltage is the current multiplied by the total impedance. The total impedance is R plus SL. So we can say that the output voltage is the impedance times the current IV. And note that all of these voltages and currents, they are currently in Laplace form. Just to remember, just to make sure that we keep the domain, the domain connection correct. And finally, when we solve equation 1 and 2, and this is the transfer function that we have obtained. It is already highlighted. It is already encircled as shown here. So IV over EI is minus 1 over RI, the whole divided by LC times S squared plus L over RF plus RC times S R over RF. So to conclude this section, I would like to point out that op-amp circuits find lots of application in analog electronics, particularly in performing the analog arithmetic such as addition, subtraction. You can even construct multipliers and dividers. So the early generation of computers, those which were built using the analog devices, the analog computers as we call them, were actually made up of op-amp circuits. And then they're also finding lots of application in the implementation of the analog controllers as well as compensators, and likewise in signal processing we see op-amp circuits used to implement the filters. So the complete details are containing some of the op-amp circuits implementation, the aforementioned application can be found in table 4.1. That's your textbook. So do go and check that out. And this is the end of our lecture on the methods and techniques for modeling electrical circuits. I appreciate your attention, and I hope you will have some questions. For that, we shall have our regular question and answer sessions on Thursday afternoon starting at 2 p.m. So till then, take care and bye-bye.